our head, Professor Imran sir, to kindly take their seat on the dais. I request conveners, Professor Saikha Ikram and Dr. Raisuddin sir, to kindly escort the guests to the seat. Thank you, everyone. Now, in keeping with Jamia's rich cultural traditions and our firm belief that any endeavor commenced with the remembrance of Almighty brings success and fulfillment, so we begin our program with the recitation of Holy Quran Pak. For this, we are honored to invite uh, Amjad sir here on the dais.
أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. الرحمن علم القرآن خلق الإنسان. الرحمن علم القرآن خلق الإنسان. خلق الإنسان علمه البيان. الشمس والقمر بحسبان والنجم والشجر يسجدان. والسماء رفعها ووضع الميزان ألا تطغوا في الميزان وأقيموا الوزن بالقسط ولا تخسروا الميزان. والأرض وضعها للأنام فيها فاكهة والنخل ذات الأكمام والحب ذو العصف والريحان. فبأي آلاء ربكما تكذبان. صدق الله العظيم. बिस्मिल्लाहिर्रहमानिर्रहीम। रहमान ने कुरान सिखाया, उसी ने इंसान को पैदा किया और उसे बोलना सिखाया। आफताब और महताब मुकर्ररा हिसाब से हैं और सितारे और दरख्त दोनों सजदा करते हैं। उसी ने आसमान को बुलंद किया, उसी ने तराजू रखी ताकि तुम तोलने में तजावुज़ न करो। इंसाफ के साथ वज़न को ठीक ठीक रखो और तौल में कम न दो। उसी ने मखलूक के लिए ज़मीन बिछा दी जिसमें मेवे हैं और खोशे वाले खजूर के दरख्त हैं और भुस वाला अनाज है और खुशबूदार फूल हैं। बस ए इंसानों और जिन्नातों, तुम अपने परवरदिगार की किस किस नेमतों को झुटलाओगे। सदक़ल्लाह।
Thank you, Amjad sir, for this enlightening recitation. Now I request Professor Athar Adil Hashmi sir to please welcome our international guest, Professor Zain sir, by offering a sapling and a shawl as a token of respect. Now I request Professor Nahid Nishat ma'am. Thank you. Now I request Professor Nahid Nishat ma'am to welcome our esteemed keynote speaker, Professor Akash Deep. Thank you. Now I request Dr. Salim Javed sir to welcome Dean Faculty of Sciences, Professor Saiduddin sir. Moving ahead, I request Badsha sir to welcome Atikur Rahman sir. Next, I request Professor Saikha Ikram to welcome our head of the department, Professor Imran Ali sir. Thank you, everyone. Next, to celebrate the spirit and pride of Jamia Millia Islamia, we will join to the soulful and melodious performance by playing Jamia Ka Tarana.
शहरे आरज़ू मेरा शहरे आरज़ू मेरा दया रे शोक मेरा शहरे आरज़ू मेरा हुए थे आके यहीं ख़ैमा चलो दीवाने हुए थे आके यहीं ख़ैमा चलो दीवाने उठे थे सुन के जो आवाज़ें रहबराने वतन उठे थे सुन के जो आवाज़ें रहबराने वतन यहीं से शौकी मेरा प्रियों को रात मिला यहीं से शौकी मेरा प्रियों को रात मिला सीने होश को बख्शा दूंगा मेरा सीने होश को बख्शा दूंगा मेरा यहीं से आए सदा यहीं से आए दिल के दाग को किस तरह रखते हैं रोशन दिल के दाग को किस तरह रखते हैं रोशन दया रे शौक मेरा दया रे शौक मेरा शहरे आरज़ू मेरा शहरे आरज़ू मेरा दया रे शौक मेरा शहरे आरज़ू मेरा मेरा शहरे आरज़ू मेरा गया रे शौक़ मेरा शहरे आरज़ू मेरा यहाँ पे शम्मे हिदायत है सिर्फ अपना ज़मीर यहाँ पे शम्मे हिदायत है सिर्फ अपना ज़मीर यहाँ पे क़िबला ईमान का बाए दिल है यहाँ पे क़िबला ईमान का बाए दिल है सफ़र है दीन यहाँ कुफ्र है क़याम यहाँ सफ़र है दीन यहाँ कुफ्र है क़याम यहाँ मेरा हरम कुदूस में मंज़िल है यहाँ मेरा हरम कुदूस में मंज़िल है शनावरी का तकाज़ा है नो बनो शनावरी का तकाज़ा है नो बनो बनारे मौत में आसूदगी ये साहिल है बनारे मौत में आसूदगी ये साहिल है दया रे शौक़ मेरा दया रे शौक़ मेरा शहरे आरज़ू मेरा शहरे आरज़ू मेरा दया रे शौक़ मेरा शहरे आरज़ू मेरा शहरे आरज़ू मेरा शहरे आरज़ू मेरा
Thank you to the performing group for the fantastic performance and for being part of this beautiful tradition. Now I invite Professor Imran Ali, Sir, Head Department of Chemistry, Jamia Millia Islamia, to please deliver the welcome address.
Respected dignitaries present on the dais, my colleagues, faculty members, and dear students, a very good morning to all of you. My own behalf and on the behalf of the department, I welcome all of you in this 5 days program, GIAN program, on the title of In-Situ Design and Catalytic Dynamics of Nanomaterials for Water and Air Quality Monitoring and Mitigation. The topic is very interesting. You can see it is an amalgam of nanotechnology and the climate. You know, nowadays the whole world is crying for green environment. So, in this regard, we need to monitor the quality of the water and the air. In the corona period, if you remember, doctors were telling us do maximum analysis of the corona, maximum testing of the corona, and you'll get rid of this calamity. In the same way, if we will do the maximum sampling analysis of the air or the water and determine the quality, then we will be able to maintain the green environment. So in this regard, the nanomaterials are playing very important role to develop the sensors and smart techniques and membranes to filter or analyze the water and the air quality. So I think the topic is very interesting and it will be very beneficial. from USA. So I'm trying to close the mobile. Anyway, so the topic is very interesting to monitor the quality of the air and water, which is the essential requirement to achieve the green environment. So uh, in this way, I believe this 5 days program will be very beneficial for our students and the faculty members because you have the chance to interact with the speakers and our foreign delegates. And let me tell you about some brief of our department. And this department was established in 1963 with the starting of undergraduate program, and later on master program was started in 1992 with material chemistry. Later on, uh, the other branches of chemistry like organic chemistry, inorganic chemistry, and physical chemistry have been started. And we all the faculty members are doing very hard work here and publishing good quality of papers and developing some good patents. I am very happy to inform you that our department has published more than 500 papers in last 5 years, and some professors are of very high impact professor here, and some faculty members have been listed in 2% list issued by the Stanford University of USA. And it is also very important to inform you that the chemistry department is very productive department, and we are contributing a lot in the national and international ranking of Jamia Millia Islamia. Based on our achievements, we have been funded by projects of crores of rupees, including DRS1, DRS2, UGC, FIST, and GIAN program, and other things. So all the faculty members are doing very good and in teaching and research, and I trust that the journey will go ahead. So with these brief words, I again welcome all of you here, and I wish all the very best. This 5 days program will be beneficial for the students and the faculty member. So thank you very much.
Thank you, Imran sir, for your warm and inspiring words. Now I invite Professor Saika Ikram, Course Coordinator GIAN, to deliver the course overview.
Thank you, Dr. Zeba. Very good morning to all of you. Before I give a synopsis to this day course, which is going to start from today, let me put my profound respect to the distinguished guest on and off the dais. To begin with, Professor Imran Ali, Head Department of Chemistry, Professor Saiduddin, Dean Faculty of Sciences, Professor Atiqur Rahman, University Coordinator GIAN, Professor Akash Dev, our keynote speaker for today's session from Institute of Nanoscience and Technology, Mohali. Professor Zain Al-Bahi, our foreign faculty from Al-Azhar University, Cairo, Egypt, who fondly addresses me as little sister with a weird accent. Professor Zain, I hope that you'll be understanding my weird accent right now. Then I put my deep regard to Professor Mehtab Alam Rizvi in absentia, who was supposed to be our chief guest, but unfortunately he has a meeting. That's why he couldn't come up and join us. But certainly he'll be joining us during the tea or in any of the evening session. Then, dear faculty, fellow faculty members from Jamia and other universities and participants from across the country, my greetings to you and warm welcome irrespective of the temperature outside. As we all know that the growing awareness of the environmental issues has created a demand for professionals with specialized knowledge in air and water quality monitoring and mitigation, offering diverse career paths in environmental consulting, government agencies, and research institutions. The same way, nanomaterials plays an important role in improving air and water quality monitoring and remediation as they enable the development of smaller, more accurate and portable air and water quality sensors as well as advanced filtration and adsorption system that can effectively capture particulate matter and gaseous as well as inorganic and organic pollutant. And if I say that we are passing through an era of nanotechnology, it's not any exaggeration. Hence, the courses in air and water quality monitoring and mitigation are crucial for understanding environmental health and implementing effective pollution control measures. They provide the knowledge and skill necessary to assess environmental conditions, identify pollution sources, and develop strategies to reduce and prevent future contaminations. About this course, which we are going to conduct covering the theme of in situ design and catalytic dynamics of nanomaterial for water and air quality monitoring and their pollution management, quite a matter of research in today's scenario. The key areas which we will be covering in the course that would be air and water quality monitoring, which would be including identification of the pollutants, particulate matters, ozone, nitrogen oxide, etc. Assessment of water parameters, for example, pH, dissolved oxygen, nutrients, heavy metal, identification of pollution sources and monitoring techniques, and analysis of quality data. Then we would be covering the mitigation strategies, their development and implementation of the measures to reduce and prevent pollution, including industrial waste treatment, emission control, and alternative energy resources. We will also take into account the environmental regulation and policies, their understanding and applying relevant environmental laws and regulation to protect air and water quality in the environment. Then, of course, the data analysis and interpretation. By providing a comprehensive understanding, this course will equip the participant with the knowledge and skills necessary to contribute to a healthier and more sustainable environment, ensuring the protection of human health and the well being of ecosystems. With this brief introduction, I wish you all a pleasant stay in Jamia. Thank you, and we are here for you for next 5 days for a thoughtful and knowledgeable discussions ahead. Before I conclude, I leave a quote from I don't know either it is from Quran or not, but I leave it to wisdom of Professor Zain to explain it to you. Allahumma la sahla illa ma ja'altahu sahlan wa anta tajhalul huzna sahlan idha shita. Sir, I leave it to you, and with this, thank you so much. Be with us.
Thank you, Professor Saika Ikram, for the detailed and motivating overview. I now request Professor Saiduddin Sir, Dean Faculty of Sciences, to deliver special address.
Professor Imran Ali, Head Department of Chemistry, our distinguished international expert of the GIAN program, Professor Zainhom Muhammad Ahmed Ali Al-Bahi, keynote speaker and the chief guest of today's program, Professor Akash Deep, Director of Institute of Nanoscience and Technology, Mohali, Chandigarh, Punjab, Professor Atiqur Rahman, Local Coordinator GIAN program, Professor Saika Ikram, Course Coordinator GIAN, esteemed colleagues, dear participants and students, Assalamu alaikum and a very good morning to all of you. It's my great pleasure to welcome you all to this prestigious GIAN program titled In Situ Design and Catalytic Dynamics of Nanomaterials for Water and Air Quality Monitoring and Mitigation. This theme addresses some of the most crucial challenges the humanity faces today, that is, clean water and clean air, and that now the cutting edge technology involving nanomaterials can serve as a catalytic solution for environmental monitoring and mitigation. The design and application of such materials are therefore not just a scientific pursuit, but a responsibility we hold towards the sustainable development and public health. Jamia Millia Islamia continues to shine as a beacon of academic and research excellence. The Department of Chemistry, in particular, stands as a top class academic and research hub within the Faculty of Sciences. In the last 5 years alone, the department has produced over 550 high quality research papers, amassing a total citation count of several thousands and achieving an impressive H index of 115. These numbers are not just metrics, they reflect the impact, quality, and global relevance of the work being done in the Department of Chemistry. We are honored to host Professor Zainham Muhammad Ahmad Ali Al Bahi, a distinguished physical chemistry professor from Al Azhar University, Cairo, Egypt. Professor Zainham brings with him a rich research background in the design and catalytic applications of nanomaterials for environmental pollution control. With over 310 SI publications and more than 7,000 citations, his pioneering contributions to environmental catalysis and nanotechnology will certainly enrich the deliberations of this program. Additionally, we are privileged to have Professor Akash Deep, Director of the Institute of Nanoscience and Technology, INST, Mohali, Chandigarh, Punjab, who will be delivering today the keynote lecture. Professor Deep is renowned for his groundbreaking work in the fields of nanomaterials for energy, environment, and biomedical applications. His presence will undoubtedly inspire and guide our participants as we embark on this academic journey. Moreover, I would like to take this opportunity to congratulate the entire Department of Chemistry for successfully organizing its fourth international academic event within the past 1 year. A commendable achievement that showcases their dedication, collaborative spirit, and commitment to pushing the frontiers of science. I am confident that during the 5 days, this program will provide a dynamic platform for knowledge exchange, international collaboration, and skill enhancement for all our participants. It is through such collective academic efforts that can pave the way towards a cleaner, healthier, and more sustainable future. Thank you, and I wish the program a great success.
Thank you, Professor Saiduddin, sir, for your valuable and encouraging words. Now I invite Professor Atikur Rahman, sir, local coordinator of the GIAN program, to deliver the introductory GIAN address.
Very good morning, Assalamu alaikum. Honorable guests at the dais, my colleagues and young scholars. It's very important and proud and privileged day today for Jamia that Jamia is hosting the second GIAN program. And the very first outset, I must say that Jamia Millia Islamia has submitted several projects, and out of that, Dr. Raisuddin is lucky enough that he has been awarded this GIAN program. Honorable Speaker of this today program, the chief guest and the foreign delegate and foreign speaker and foreign expert, Zain Muhammad Al Bahi from Al Azhar University, Cairo, Egypt, on behalf of Jamia Millia Islamia, on behalf of our Vice Chancellor, and on my own behalf, I welcome you, sir, to this important and prestigious academic event. Professor Akash Deep, Director Institute of Nanoscience and Technology. Sir, welcome to this program, and we'll be having your input and your insight on this topic, and my participant will be very happy to listen you. Professor Saiduddin Sahab, the Dean Faculty of Science, Imran Ali Sahab, Head Department of Chemistry, the course coordinators, Dr. Raisuddin and Dr. Saika Ikram, and all my other colleagues and young scholars. Let me give you a brief glimpse of the GIAN program, what exactly it is. So it was way back during retreat of IITs with the then MHRD Minister Srimati Zubain Irani on June 2014 at the Goa. It was decided that a system of guest lecture by internationally and nationally renowned expert would be evolved along with the comprehensive faculty development program not only for the IITs, IIM, and IITs, but for the other universities across the country. Unquote. So this was the motto that was conceived way back in 2014. And then after that, at the time the ministry was MHRD, Ministry of Human Resource Development, they started this program, a very unique program. And I must say, I always say off the record and with the friends and colleagues that this present government, Honorable Shri Narendra Modi ji has started, and that is very unique. The fundamental concept of this program is that such large number of young students cannot go abroad because of the certain reasons. So it is good to have a one person who can come to an institute and can enrich these young scholars, not theoretically but also practically. That is the entire motive of this program. So Government of India approved this program, unique program, that is called Global Initiative of Academic Networks in Higher Education, which is aiming at tapping the talent pool of scientists and entrepreneurs internationally to encourage their engagement with the Institute for Higher Education in India, so that augment of the country's existing academic resources, accelerate the pace of quality reform, and evaluate India's scientific and technological capacity to global excellence. So this is one of the key capacity building program. There are about 60 students that those have been selected for this program, apart from many other those who applied. So this was the one. In order to garner the best international experience into our system, in the Indian education system, sir, to enable interaction of students and faculty with the best academic and industry experts from all over the world, and also share their experience and expertise to motivate people to work in the Indian problem. And the problem that what rightly has been taken by Dr. Isuddin and you, that on the nanotechnology material and the air and water quality. So it has a headquarter. It used to be headquarter at IIT Kharagpur. Now it has been shifted to IIT Hyderabad in the last 1 year. They coordinate. If I tell you the key objective of this program, number one, the GIAN program objective to provide opportunity to our faculty to learn and share knowledge and teaching skills in cutting edge areas, which is one we see here, cutting edge technology. Number two, to provide opportunity to our students to seek knowledge and experience from reputed international faculty like you, sir. Number three, opportunity to the students of the different institute, universities to interact and learn the subject in niche areas through collaborative learning process. Number four, to motivate the best international experts in the world to work on the problem related to India. Number five, develop high quality course material in niche areas both through video and print that can be used by a larger body, students and teachers. And last, to document and develop new paradigm methodology in emerging topics of national and international interest. So this is what we have. This course is being recorded and it is live across the country. So it used to be earlier also, but now they are putting it live. So this is what the number five, the objective that the GIAN is this program that has been designed by the Ministry of Education now. Earlier it was MHRD. They have said that through video and print that can be used by larger body of student and teacher. Those who have not come here, they can see and they can learn and they can get enriched on the issues and things what you are going to deliver. Not only for today, for the entire 5 days program. Earlier it was repository that was recorded and put it on the ministry and UGC side, they put it. But now it is live and it will be keep on the open domain for the students and faculty. There are 13 broad areas of GIAN program, sir. Number one, I put it in short. I'll not take of all name. Architecture, design, planning, and heritage. Chemical and biochemical science, under which this program comes. Earth and environmental sciences, electronics, electrical, information and communication technology, humanities and liberal art. It is not only limited to science, but humanities, liberal art, life sciences and health. Law, management, mathematical, computer science, mechanical science and infrastructure, physical science and social sciences, sir. Other categories and interdisciplinary categories, which does not fall in this. So that can be classified. So each and every faculty is eligible, each and all the universities and colleges are eligible. Those who have come under 200 ranking of the India's within the university, they are eligible to apply for the GIAN program. The funding for this program is one of the best. For 1 week program, 5 days program, they fund for $8,000. That comes to 6,44,000 something at the rate of 83 rupees per dollar. So funding is enough. And for the 2 week program, sir, where we have the 24 to 28 lectures has to be delivered. For that, they have $12,000 funding for the entire course duration. And this funding is used for your travel, sir, your honorarium, your hospitality, everything is free. And I'm sure that the coordinators must be taking due care your stay and after your program. So funding is fair enough. That is very good, sufficient amount of money. If I give some data, sir, so as per GIAN data that is released, this is the fourth phase. During phase 1, 2 and 3, they approved about 2,163 courses. Out of that approved courses, 1848 courses were completed. Some could not be completed because of certain reasons that maybe have, their institute must be having. And I'm very happy that the data what I have got it from the ministry that the about 1,654 number of unique foreign faculty were associated. Imagine, sir, in the last 4 5 years, 1,654 faculty were they came, visited India, different institute, universities, ITs. It was not only limited to ITs, but all the universities, even the state universities are also eligible to apply. And then when they get approved, they have. And about 72,000 number of students and faculty members trained. Imagine 72,000 in last 45 years. And therefore, I said this is very unique and important program that has been started by present government. No, this is very new. If I talk about the data in Jamia during phase 1 and 2, Jamia got 31 courses, which is just after the ITs and IM. I'm very proud that 31 projects was approved during program phase 1 and phase 2. So we were one of the best universities where the maximum number of GIAN programs were sanctioned. That was completed. And then in phase 3, 42 GIAN proposals were submitted by our young and learned faculty members. But वो कोरोना के भेंट चढ़ गया. Then the corona came. We submitted in 2018 and 19. Corona came and everything is washed out. And I'm sure that if it could have been gone through the review process, so 42 out of 42, I'm sure that 25, 30 must have been approved. But the ministry said that you revise it and then submit it. So out of 42, 5 GIAN and MOOCs program were approved in the initial phase, and then it was a lockdown. In phase 4, the ministry received 779 courses and 339 were approved by the ministry, and some of the courses is already completed, some will be completed in due course of time. In phase 4, what we have in phase 4, Jamia submitted 11 proposals, and it was less because it was a very short time. Ministry quickly closed the date in September. So out of 11, 3 projects were approved. So it is fairly good number. 33% proposal approved. So as Imran Ali has the head department of chemistry has said, chemistry department is one of the best, and that shows that chemistry department has got one proposal. And for that, I must congratulate Saika and Raisuddin. We should give a big round of applause for both of them. And sir, Dean sir, I must tell you that, and director sir, I must tell you, very good proposal submitted. But we could have got some more. But because of some reason, for shortage of fund or something, we could not get more. So I must congratulate Dr. Saika, Ikram and Raisuddin that they have chosen, and sir, you have chosen a very important topic, that is air and water. And I always say to my students, water is elixir of life. And next comes is the air. So this is one of the prime target of sustainable development goals, where we talk about clean water, SDG 6. When we talk about clean cities, that comes under the SDG 11, that is air. So in that context, I must say that this program will be a very good one, and I wish the participant and the course coordinator entire department for a successful completion of this GIAN course. Thank you so much.
Thank you, Professor Atikur Rahman sir, for setting the tone of this program. It's time now for the keynote address by our distinguished chief guest, Professor Akashdeep sir, Director of Institute of Nanoscience and Technology, INST Mohali. Professor Deep is a renowned scientist in the field of nanomaterials for energy, environment, and biomedical applications, whose work has significantly contributed to technological innovations. I now request Professor Akash Deep sir to please deliver your keynote address.
Thank you, honorable guests on the dais, faculties, students. Uh, it's my pleasure to be here in this university and to talk about this program, GIAN program, on the very important topic of the monitoring and mitigation of environmental pollutants, air quality monitoring, water purification. It's water and air. These are two parameters, which drive our life. So, in recent decades, because of the industrial activities and many other things, air and water are being polluted to great extent. There's no stopping. So, what the need of the hour is to ensure that we maintain a quality control on by assessing the different parameters of air and water, as well as on the same time we should also devise methods to purify them. Uh, the use of nanomaterials is very exciting. It provides a lot of opportunities. The high surface area of nanomaterials, the activity of the nanomaterial that helps in developing methods which offers us more efficiency than other conventional methods. The detection of the parameters in air and water, it's not a local problem or a national problem. It's a global problem. Everywhere the devices are required for the monitoring of air and water quality. And it's if you uh, I talk about the students, so the students have a lot of scope, not only academically but also the development of technologies that can be commercialized, because there's a lot of demand of such technologies in the market. Conventional technologies are there, for example, you chromatographies are there. Then we have, yes. So I was talking about the technologies that are available and that can be developed. So the need of the hour is to develop the portable technologies that can be taken to the field. We have the technologies that are applicable at a lab level, but now because we have a lot of samples everywhere, there's a need of monitoring and detection as well as the purification. So the idea should be to develop the technologies that can be taken to the field itself, portable technologies. And the methods of purification should be rapid, sustainable. The materials that we use should be recyclable so we do not generate any further waste. Hmm? So the talk that because I don't have much time here as per the note sheet, so I have 15 to 20 minutes. I will be covering some of the important work that we have been carrying out in our lab uh, with regard to the application of sensors in the detection of environmental pollutants. So can I have a pointer? Okay, no, okay, it's okay. I can start with. So I just point with. Oh, thank you. So I come from the Institute of Nanoscience and Technology because I am representing this institute. It's my duty to introduce you to you about our institute a bit. It's not. Oh, it's you. Eh, उसी से हो रहा है? Okay, okay. So our institute was established in 2013 and with a vision of working on basic areas and of course the areas which can be translated into technologies in the area of nanoscience and nanotechnology. So these are the missions and objectives. The objectives basically to develop technologies and also to create the human resource in the area of nanoscience. So if we talk about purely in the area of nanoscience, this is the first and only institute that has the mandate to work on nanoscience and nanotechnology in India. So we are around 37 faculties there, and we have 250 students. Apart from this, we have also some project staff and other faculties. And our key research areas are basically in the three sectors: energy and environment. Then we have quantum materials and devices unit, and we also work on healthcare and agriculture. So it's no, here we can. I have mentioned the ranking of our institute. It's 21 in all sciences in India, and amongst the DST institute, we are second in India. So it's quite a good ranking, considering that we have only 37 faculties there in whole INST. And after JNCSR, we are the second ranked institute. So we have different key R&D facilities here. So if you want to access these facilities, or you want to utilize these facilities on payment basis, or also on the collaborative basis, we can offer you the assistance in these areas. So talking about the environmental pollution, everyone is aware about the environmental pollution, the problem with. So there are different types of environmental pollutions, but majorly air pollution, water pollution, soil pollution, noise pollution. So air pollutions can be due to the gases, different volatile organics. Then in water we can have the presence of organic pollutants, microorganisms, other heavy metals, etc. In soil also we have nowadays the presence of a lot of heavy metals. So all these heavy metals from soil also goes to the water as well as to the air. And hydrocarbons are also there. So the concentration of these pollutants could be from microgram to nanogram per ml, and depending upon the categories of the pollutants, the maximum permissible limits could be from microgram per liter to nanogram per liter. Yeah. So sources of pollution and fate of pollutants, you must be aware of this thing. This is not new, but I just wanted to emphasize that through different routes, exposure, intake, uptake, we can be affected. So we can be affected from different types of pollutants, and ultimately these pollutants can have different health disorders, like respiratory, neurological, and other dermal type of problems we can have because of the pollutants. Normally, the pollutants are analyzed by chromatographic methods, then electrochemical techniques are there, spectrophotometries are there, chemiluminescence and fluorescence methods are there. But the problem is they have some limitations. Now, as the sampling is too large, we have large numbers to analyze, of samples to analyze, different types of samples, water, even food, and then milk, different samples. So for that purpose, we need some technologies that are less laborious, that can be taken to the field itself, and they that need minimal sample requirement. So for that purpose, the concept of sensors comes into the play. What are sensors? Sensors are the smart devices that are used for direct measurement of physical quantity of analyte in a sample matrix. So the advantages of sensor is that the tests are conducted at the site itself. They provide very rapid results, and the cost is very less compared to the conventional technologies. So biosensors are also kind of sensors, but they contain a biorecognition element. So what biorecognition element does? It provides the selectivity to any analyte. For example, I want to detect E. coli in water. So the sensor should be specific to E. coli only. So for that purpose, I need to add one particular element to the sensor surface that detects or captures that bacteria only. So for that purpose, in biosensors, we attach biorecognition elements, and there could be different transducers, could be optical transducers, electrochemical transducers, and then the signal processing is done in miniaturized devices, portable devices like your glucose monitor. So the sensors provide very rapid results, and in very less time. So different types of sensors for pollutant detection have been developed over the years. For example, nanomaterials based microelectrodes. Then we have some interdigited microelectrodes, microfluidic sensors, miniaturized screen printed sensors. So these types of devices provide a very good alternative to the conventional methods. How we can develop a sensor? Developing a sensor needs some steps to be taken out. For example, if I have a nanomaterial, and this nanomaterial has to be made selective to a particular specific analyte. So what I'll do, I'll conjugate it with some antibodies or some nucleic acid or any other, it could be any specific ligand as well. That will make the sensor specific to that particular analyte, and then that material will be coated on thin films, or it can be coated on optical fibers, or it can be simply used as liquid form itself, or in electrode form, or any other kind of form. And then this sensor can be used for the analysis of different analytes. So depending upon the nature of analyte, we devise how this sensor is going to be developed, what nanomaterials we need, if we need the recognition element or not, what could be the signal processing time, or what is the energy requirement, do we need to uh, do the test qualitative only or quantitative only. If the qualitative means just the presence of the analyte in yes or no manner is required, then we can simply use optical methods like litmus paper test for pH. So like pH is tested by checking the color changes. We can develop such kind of paper devices for different type of analytes. So there are different factors that are needed to be considered when we develop any sensors. There could be environmental factors, there could be contaminant factors, material types, and analysis. So a lot of factors have to be optimized and tested during the process of sensor development. So I will skip this. So in our lab, we are carrying out the research on the development of sensors for analytes, or you can say pollutants like pesticides and heavy metals and bacteria, pharmaceutical drug residues, etc. And we basically use 2D nanomaterials. The 2D nanomaterials are very they have very good electrochemical activity, and they are large surface area metal and easier to be produced in bulk also. Also, we are using metal organic frameworks. Metal organic frameworks are porous materials, and sometimes they can be made specific just by pore engineering. We can selectively tune the cavity sizes of MOF so that only a particular gas or particular analytes is trapped within the network of MOFs. So that's how we achieve the specificity, even without the requirement of any biorecognition elements. So here you can see the advantages are mentioned. I have already discussed this, but the important thing to see here is the specific surface area of MOFs. So because they are porous, they have a very large specific surface area, close to 7,800 meters square per gram. One MOF has been reported. Generally, this value could be in the range of 500 to 8,000 meters square per gram, depending upon the metal ion and the linker, which is used to fabricate these metal organic frameworks. So I'll not go into the details. What are the parameters that are to be considered when we develop these sensors? I'll just demonstrate some of the examples that these are some sensors that we have developed to detect different pollutants, or you can say analytes also, some disease markers as well. So here you can see there are some screen printed electrodes. So different types of sensor formats have different applicabilities. So if we want to detect the analytes that are like in microgram per liter range, so for that purpose we can use screen printed electrodes, because the concentration is somewhat in the microgram or micromolar range. But if the concentration is nanomolar range, our detection limits are needed to be that low, then we use interdigited electrodes. They are like field effect transistor electrodes. Then for the gases, we can simply print our materials on A4 size papers or optical fibers. So just by observing the change in the color, for example, if ammonia is there, this paper will turn into yellow or green. So this will give an indication that yes, this toxic gas is present in our sample. then we can simply have some solutions. For example, if you have this solution, buffer solution, you want to detect the presence of any bacteria, then you introduce the bacteria in the solution. This solution will turn its color into blue. And this can also be determined photoluminescence spectrophotometrically, and we can both quantitative and qualitative tests can be done. Likewise, in this example, what we did, we simply synthesized with this MOF, and we conjugated this with antibodies, and this was the color change. So fluorescence. So the fluorescence is reducing as the bacteria is introduced into the solution. So very simple. Just by observing the change in the fluorescence, we could determine the presence of bacteria up to 2 to 3 CFU per ml. In this case, an enzyme, because enzymes are the catalysts, they can catalyze certain processes. So, for example, if I want to detect methyl parathane, I can use this organophosphate hydrolase. This organophosphate hydrolase will convert that methyl parathane to PNP, and this paranitrophenol will give an absorbance at 410 nanometer. So, just by observing this change in the absorbance, using a simple UV photometer, we can determine the concentration very selectively and with high sensitivity. So these are the examples that the sensors we developed for nitrobenzene. Again, very simple method of observing the change in the fluorescence. Here also, I can skip this. This sensor was for SORES. Again, the change in the color of the solution, it provided us the way of determining the concentration of SORES in the sample with a very high detection limit, 39 CFU per ml. So this was an example in which we developed magnetic nanoparticle coated MOF. And what is the beauty of this sensor? That it can isolate the bacteria with the application of simple magnet here from the solution. So we can very selectively separate different bacteria. And also when we separate this, we can check the fluorescence intensity of the solution. So the fluorescence intensity of the solution is directly proportional to the concentration of bacteria. So it provides us both separation as well as the detection, purification and detection of bacteria in the solution. Likewise, this method was developed for the detection of copper. Very simple method. Again, we can see the turbidity change of this solution. This solution was of MOF modified with L-cysteine. And you can see as the copper is introduced in the solution, the color is changing, the turbidity is changing. So, and also the fluorescence is changing. So the different modalities are there. So either we can simply observe the turbidity change or color change, fluorescence change, as well as the here fluorescence changing. Also, this can be integrated into microfluidic channels, and here you can see we introduce one drop of water here, and different concentration could be detected on this water paper sensor. Then we also have some thin film sensors which works on the electrochemical signal. So here you can see this is atrazine pesticide. So again, our idea is always to develop simple sensors. So here we have a electrode here. So we provided some bias potential, and we observe the change in the current. So the change in the current, actually this is a copper MOF modified with polyaniline, and then antibodies were conjugated. So here you can see that the sensitivity of this sensor is very high, and it is also specific only to atrazine because of the antibodies. Then again, this was a sensor developed for E. coli detection. Same analyte, we can determine 24 samples. So this provides a very rapid detection, and the sensitivity of this device is also very, very low. Again, I can skip this because the lack of time, but just to show that SPR methods, surface plasmon based SPR methods, can be translated onto optical fibers, and this is also again a very simple tool which can also be reutilized. We can simply wash away our analytes from the surface of this fiber, and this can be reutilized for up to 10 cycles. So the sensitivities of this types of sensors is also very high, and we have developed these sensors for some bio medical applications. So I can conclude my talk with some points that the nanomaterials like MOFs, CNTs, graphene, polymers, they are excellent materials for sensor development because of their large surface area and the presence of functional group over them. So the functional group are needed to attain the specificity. We need to conjugate them with biorecognition elements and other things. So for that purpose, the 2D materials and other nanomaterials, they are excellent materials. They can be converted into sensing papers, kits, strips, solution electrodes. So different formats of sensors can be developed. They provide large surface area, and therefore we can match the sensitivity to the levels of conventional techniques like HPLC or GC. Multiplexing capabilities in modern sensors are also being explored. For example, a same sensor chip can be utilized for the detection of multiple analytes in one go. So that will reduce the cost of the analysis. Uh, One of the challenge in this area is the scalable and controlled production of nanomaterials. Of course, we can synthesize the nanomaterials in lab scale quantities, but once we want to convert these methods into technologies, what we need the availability of nanomaterials in bulk scale. So the quality control on the production of nanomaterials at that scale is a challenge which needs to be addressed still. So thank you very much for your kind attention. I rushed into my presentation because of the constraint of the time, but if there is any question, I would be happy to answer. Okay, thank you, thank you, thank you, thank you. Thank you.
Thank you so much, Professor Akashdeep, sir, for your engaging, enlightening, and thought provoking keynote lecture. Now, before I invite Professor Zain home for his inaugural address, I take this opportunity to introduce our international faculty. So, Professor Zainhon M.L. Abai, he was born in Egypt and he worked as researcher in Catalytic Research Center at Japan from period 2000 to 2003. He worked as postdoctoral fellow in Engineering School Osaka Prefecture University, Japan from a period during 2007 to 8. He served as head of department, chemistry department at Taif University, Taif, Saudi Arabia from 2008 to 17. And presently, Professor Zain is working as physical chemistry professor in the Faculty of Science, Al Azhar University, Cairo, Egypt. His research interests include design, preparation, and characterization of nanomaterials and their impact on the catalytic activity towards the degradation of air and water pollutants. Currently, he is interested in the preparation of core shell nanocomposites and investigating their activity in different applications with the aid of various sophisticated spectroscopic techniques. Uh, as already mentioned by our dean, he has over 310 citation publications in various peer-reviewed journals and over 7,000 citations with an H index of around 45. With these words, I would request and invite Professor Zain for his inaugural address.
Assalamu alaikum. Thank you very much for inviting me for this prestigious GIAN program. And actually, as you have just heard, that I am Zinhum Ilbahi from Egypt, Cairo, Al Azhar University. I am very happy to join you in this program, and inshallah, we will learn together in these 5 days. And inshallah, everybody will be happy. Everyone will have a good time, inshallah. Later, we will have much more talks and discussions. and I am here for any scientific or cultural discussions with Indian people, because it's a very good chance to close our cultural and habits together. Inshallah, we will enjoy together, inshallah. Thank you very much. Thank you.
Thank you, Professor Zain, for your valuable and insightful thoughts. Uh, Now it's time for the vote of thanks, and for this, I invite Dr. Raisuddin Sir, Gyan Course Coordinator.
Thanks, Dr. Zeba. A very good morning to this August gathering. It is my privilege and honor to deliver the formal vote of thanks at the inaugural ceremony of GIAN program on in-situ design and catalytic dynamics of nanomaterials for water and air quality monitoring and mitigation. First and foremost, I would like to express my sincere gratitude to the Ministry of Education and GIAN Execution Committee for their endorsement and financial support, making this program a reality. I am profoundly thankful to our Honorable Vice Chancellor, Professor Mazhar Asif in absentia, for this constant encouragement, support, and inspiring leadership. I extend my heartfelt thanks to our esteemed chief guest, Professor Mehtab Alam Rizvi, Registrar Jamia Millia Islamia in absentia. His guidance are always a source of motivation for us. My sincere appreciation goes to Professor Saiduddin, Dean, Faculty of Sciences, for always standing by the Department of Chemistry in all our academic endeavors. I am grateful to Professor Imran Ali, Head Department of Chemistry, for his continuous support in the successful organization of this program. I would also like to take a special moment to express my deepest gratitude to Professor Atikur Rahman, local coordinator of GIAN program. It is truly his motivation, encouragement, and guidance that enabled me to conduct this GIAN program today. I place on record my deepest gratitude to our distinguished international speaker, Professor Zainhom Muhammad Ahmad Ali Al Bahi, for accepting our invitation and for sharing his invaluable knowledge and expertise with us today. Your warmth, humility, and passion have left an unforgettable impression on all of us. A special thanks to our keynote speaker, Professor Akash Deep, Director INST Mohali Chandigarh, for gracing the occasion and for delivering a highly inspiring and enlightening keynote address. I would also to thank all my senior colleagues of Jamia, friends, our faculty members, staff, and students of the Department of Chemistry for their unconditional support, dedication towards the smooth organization of this event. A special word appreciation for the course co-coordinator Professor Saika Ikram for her hard work, dedication, and meticulous planning behind this successful program. My heartfelt thanks to technical team of Jamia for providing seamless logistic and technical support. Last but certainly not the least, I sincerely thank all the participants from various institutions, different states, scholars, and invitees for their actively participation. Without your presence, this event would not have been enriching. I truly hope that this GIAN program will be a memorable and fruitful academic experience for everyone. Thank you once again and wishing you all a wonderful and engaging GYAN program ahead. Thank you very much.
Thank you, Raisuddin sir, for your gracious words of appreciation. Now, as we reach to the conclusion of this inaugural session, I request everyone to kindly rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
So, before we conclude, please allow me to leave you with a thought that resonates deeply with the spirit of scientific inquiry. This is a quote by Albert Einstein, and it is: the important thing is not to stop questioning. Curiosity has its own reason for existing. So, may this curiosity that brought us together today continue to inspire discovery and innovation. With these words, I'd request everyone to gather for a group photograph outside this committee hall. And thank you all. After the group photograph, I cordially invite all of you to join us for the high tea, which is outside the auditorium. Thank you. It is now the time for much anticipated our lecture by distinguished foreign faculty, Professor Zainhum Muhammad Ahmad Al-Bahi sir, and he's going to speak on the topic Introduction and Basic Characteristics of Catalysts. Thank you, sir.
Assalamu alaikum. Welcome today in our meeting. Okay. Welcome today in our meeting in GIAN program. Assalamu alaikum. Today, inshallah, we will start our program, which is it's according to GIAN GIAN organization. It's a collaboration between Egypt and India, Al-Azhar University and Jamia Millia University. This is a collaboration between Professor Zain and Professor Rais Dean and Professor Saika. And the title of the proposal is In-Situ Design and Catalytic Dynamics of Nanomaterials for Water and Air Quality Monitoring and Mitigation. Actually, to go through any of these topics, which is nanomaterials and water quality or air quality, whether it is monitoring or mitigation, and we should know about what is we have an introduction about catalysis. Catalysis, it is known that catalysis is a magic science. Why it is a magic science? Because it simply transfers some materials which are useless materials or chemicals to very important products. Let's have a look at this science. This is what is a chemical reaction? Chemical reaction transfers some chemicals to other chemicals. Some chemicals which is not useful to more useful chemicals. But for catalysis, we have to distinguish between the difference between catalyst and catalysis. This is the first thing we have to know, that what's catalysis and what's catalyst. Catalysis is the process itself. It means that catalysis means like transformation, the process. However, it is what's a catalyst is the tool which is the tool which is doing this process. A catalyst is a substance that affects the rate of a chemical reaction. Of course, you know that catalysts have different, we can say that catalysts have different catalysts have different definitions. Let's have a look to these definitions. But basically, we have to know that catalyst is the main, is the backbone of industry, of chemical industry, because without catalyst, a chemical industry depends on 90% of chemical industry depends on catalysis science. As we know that what is the production of catalysis? Catalysis maybe will help in production of fuels, will help in production of fuels like gasoline, diesel, heating oil, or something, and will help in plastics, synthetic plastics, rubbers, fabrics, and so on, will help in energy production like hydrogen and fuel cells, will help in emission, to get rid of emissions, which is SOxes and NOxes and etc. Will help in the polymer synthetic like adhesives, coatings, and etc. Will help in medicine, like pharmaceutical industry as a whole, will help in food production, and also will help in enzymes, because enzymes itself is a catalyst, and the enzymes will had been created since the creation of human body or human beings. This is the applications of catalysis. Of course, it is explained here. I'll not talk about it again. Let's skip it. And what is these are some definitions of catalyst, because catalyst itself is a substance that affects the chemical reaction or affects the rate of chemical reaction and helps to transfer some products, some chemicals to useful products. This is the main idea. Other definitions, many definitions have talked about it, but all are going to the same point. Some are talked in detail, and some are talked briefly about it. Let's have all of these are briefly are brief definitions of catalyst, but this one is an interpreted definition of catalyst. Catalyst is a substance that transforms reactants into products. This is the main idea. Through an uninterrupted. Uninterrupted means it is not always continuous. Uninterrupted. You can't. It always continuous from cycle to another one, and you can't. All steps are going to another step, and so on. And repeated. Repeated means always continuous cycle of elementary steps. Elementary steps in which the catalyst participates. This is a very big point. Participates. Whether is the catalyst interfere or participate or react with the reactants or not. Participate. We will check and discuss about these points. While being regenerated, participate and regenerated. It should be in its original form, regenerated in its original form at the end of each cycle during the lifetime of a catalyst. This is a little bit explained definition, but it is, of course, it has some expressions which express what is catalyst is. In general, catalysis provides, this is the most important statement, catalysis provides sustainable and cost-effective methods. Why? To transform raw materials into valuable products. This is the main goal of using the catalyst. Here is, we will discuss what is the difference between catalyzed reaction and the uncatalyzed reaction. This is the uncatalyzed reaction, what it talk about. A plus B equals C plus D. What happens in uncatalyzed reaction? Like whenever you make titration, for example, HCl plus NaOH, something like this. Reactants are going to reactor with solvent, which is water mainly. This uncatalyzed reaction will occur. It gives some products and side products through using an amount of energy. As you can see, there is amount of energy is used like this. It gives a side product and some product. Of course, you can see from this slide that you have reactants and solvents going to the reactor. Whatever the reactor is, it may be very small tube or very big cylinder of in a factory or a plant like this. This uncatalyzed reaction occurs in a reactor. Anything can be a reactor, whatever the reaction occurs. It gives side products and products. You can see here, side products are a little bit larger than products, and you can use energy. And let's see what is catalyzed reaction. In catalyzed reaction, the case is different. Why? We can reactants plus solvent and the catalyst. It goes to the reactor where catalyzed reaction occurs, and little amount of energy is used. Products and side products are coming out. You can see products and side products are coming out. Side products are, I think this is opposite. Side product should be on the top. Side products are smaller, and the products are higher one. Catalyst also recycled, and the reaction will come again and will be done again. As we can see, as we just mentioned before, it is repeated and interrupted, always cycle. We will explain in upcoming slides, inshallah. There is a comparison between catalyzed reaction and the uncatalyzed reaction. We can see here that it's like when you walk from one city to another. Of course, you can walk. Once there is a road, you can walk. If you want to go from New Delhi to another city, for example, once the government makes a road there, you can walk. It's okay. The problem is how fast you will transfer from this city to the other city. This is the problem. If you will walk, just walking, this means you may take, if it is 100 kilometers, for example, you may take 1 day or 2 days to go there. But if you use a bicycle, you can take it in 2 hours or 3 hours. It's up to you. But if you use a car, you can take it definitely less than 1 hour. But what if you will use an aeroplane? This means you can take it in few minutes. This means that the car or the bicycle or the aeroplane is the catalyst which transforms what is allowed to be transformed. This means if there is a road, this means you can go. But whether you are going as walking, or you are going with a bicycle, or you are going with a car or whatever, once there is a road, please remember, once there is a road there, if there is not a road, if there is no road for between cities, so you can't go. I will just explain this in after a few minutes. Energy needed for the for energy needed for catalyzed reaction is low, but for energy needed for uncatalyzed reaction is high. Side products is low in catalytic reaction, and for side products is high in uncatalytic reaction. The products is high for catalytic reaction, and the products is low in non-catalytic reaction. This is a brief comparison between the catalytic and the uncatalytic reaction. I hope it's understood. Now we will go to what is the basic characteristics of catalysis. There are some fundamentals connect all the catalytic idea or catalysis in together. What are these connections or what are these characteristics? The first one is what I just explained right now, the road between two cities. If there is a road, you can go. What is the road here? The road here is thermodynamics, which explains, which allows you, if this reaction can occur spontaneously, this means there is a road between the two cities. This means it can be done thermodynamically. It should be thermodynamically favorable reaction. What is thermodynamically favorable reaction? Thermodynamically favorable reaction, which is spontaneous reaction. Again, same question. What is spontaneous reaction? Spontaneous reaction which has delta G equal negative value. So any reaction has delta G equal negative value, this means it is spontaneous. This means catalysis may occur, may have a role in this reaction. But if this reaction has delta G equal positive value, this means this reaction is not spontaneous, which means this reaction can't proceed even you add a catalyst for this reaction. Okay? And there is another problem. If sometimes you add, sometimes there is a non-spontaneous reaction, and you add a catalyst, and the catalyst is okay. It will work. At this time, if you remember, your teacher or your professor asked you to do something. Oh, just try to increase temperature little. It may work. Just of course he would ask you to increase temperature. This is the key. Where do you transfer, or where you can transfer the non-spontaneous to spontaneous to spontaneous reaction. I will explain now. Now, again, I can say catalyst can increase the rate of only those processes or reactions that are thermodynamically favorable. Again, it's here thermodynamically favorable, which has delta G equal negative value, whereas delta G, if possible, it is non-spontaneous and the reaction will not go even if you add a catalyst. Of course, we measure what delta G is negative or positive from this equation, which is Gibbs equation. So this is a question: how can we change spontaneous to non-spontaneous reaction? Of course, I will explain it briefly. Delta G equals delta H minus T delta S. Delta S is the entropy change. Delta H is the enthalpy change. Of course, this term T delta S, if more negative, more positive, its value is more than delta H, this means this value will be negative, or positive will be negative value. If this term is more than delta H. So you can increase this term or decrease it by decreasing or increasing the temperature. Okay? Fine. I may recall the information that thermodynamics says nothing about the rate of reaction. If you remember, your teachers or your professors, always when they explain or study thermodynamics, they didn't mention about time. Time has no presence in thermodynamics. So kinetics is different from thermodynamics. Yes, because kinetics may discuss about time. If you increase time, this means rate, this means kinetics. But thermodynamics doesn't have any information about time or the rate of transformation. Okay? So this thermodynamics says nothing about the rate of reaction. And please, what is the definition of catalyst? Again, definition of catalyst is it helps to increase the rate of chemical reaction to give products. This is the simplest definition of catalyst. Okay, so catalyst increase the rate. Catalyst changes the time. This means it has no relation with thermodynamics. Then catalyst or catalysis science has no relations with thermodynamic functions. However, catalysis affects time, means affects what? Kinetics. Okay? Thermodynamics only give an answer about will a reaction occur, that's all. It doesn't give any information about its rate. Okay? However, kinetics answers the question. If the reaction occurs, then how fast it will be. So we conclude that catalysis is a phenomenon related to kinetics, whereas catalysis is not related to thermodynamics. Okay. Second function or second characteristic is the catalyst decrease the time to approach equilibrium. For in equilibrium equations, A plus B equals C plus D plus or minus heat. What is plus or minus heat? Do you remember? Plus or minus heat means heat is either it's a product or it's a reactant. Okay. If we have a reaction, reactants at the beginning is maximum and the products is minimum, 0. With time, reactants decrease, and products increase until we reach a point which is equilibrium point. Okay, at equilibrium position or at equilibrium point, we have two points, which is the time of equilibrium, and second is the equilibrium position. Both of these 2 points are different. How they are different? The difference is this time is related to kinetics, but this position is thermodynamic position, thermodynamic parameter. Okay, that's why this position doesn't change in presence of catalyst. However, time, which is kinetic parameter, is will change by adding a catalyst. And there is a question I can ask you now, which is, will a catalyst change the forward and backward reactions? Because as you can see here, that A plus B gives C plus D. C plus D starts to be reactants to react together again and give A plus B. Okay? These two opposite reactions. Will a reaction increase the rate of forward reaction only? Or will increase the backward reaction only? Or will increase both? Or will not affect any of them? I think I will leave this for you to just think about it, and I am sure you will have an answer. Okay? Okay, I'll answer it. Catalyst will increase both directions. Will increase both forward reaction and the reverse reaction. Okay? To get fastly to the equilibrium point. And the third characteristic is the catalyst decreases the activation energy. What's activation energy? Activation energy is the energy required, or the energy barrier required, energy barrier that should the reactants overcome to go to products. Okay, and the reaction always the catalyst always decrease the activation energy. Activation energy is kinetic parameter which is affected by the presence of a catalyst. Okay. Activation energy is, its symbol. The activation energy determines how fast a reaction occurs. The higher activation barrier means higher activation energy, means the lower the reaction rate. Okay. However, the lower the activation barrier, if it becomes lower with adding a catalyst, the higher the reaction rate. I don't know if you did it or not, if you escaped from school when you are young. If the wall of the school is a little bit high, nobody can escape, right? This guy is laughing. That means he was escaping when he was young, okay? And if this wall, which is the energy barrier, becomes lower, more people may go outside, okay? If it vanishes at all, everybody will go outside. Of course, I would like to remind you, in this pattern or in this profile, increasing the collisions will increase increasing temperature will increase collisions, which will have successful collisions, and more reactant will react. So briefly, I'll give you an idea about the collisions. There are the collisions. If a reaction occurs, then collision should be there. Collision should have two factors or two conditions. The first condition is it should have right orientation. The second is it have enough energy. If it has wrong orientation, that means no reaction will occur. And if they have two conditions, energy and orientation. It's like this pin. If you have this pin, okay, if I just click like this for tomorrow, will this piece will go to inside this piece or not? This is wrong orientation, okay? But also, it should have right orientation. But also, it should have enough energy. This means if I add it like this only, it's very easy to go outside like this. But if I add it with enough energy, this means it will not go out. Okay, this means this is the two conditions of collisions to be successful. The other is we go to catalyst activation energy. Catalyst decrease activation energy. Of course, if we have a reaction like A plus B equals C plus D like this is a reaction profile. This is the time or reaction progress. It goes like this. Collisions starts and more collisions, and here we can have transition state. This transition state go to products or will form products C plus D, and we can here. This is the zero energy, and this is the activation energy delta E, and this is delta G, which is the thermodynamic function. This is uncatalyzed reaction. But what will happen if we use a catalyst? This is the case if we use the catalyst. Activation energy decreased. But what can you see in this figure? We can see that first of all, activation energy decreased. Second, delta G, which is thermodynamic function, did it change or not? It didn't change. Thermodynamic function didn't change, delta G. However, delta E, which is a kinetic function, it changed already. And there is a third characteristic of this figure I can see, which is both profiles are the same pattern. Always, this means they went to the same mechanism, okay? And here we have another question, which is, can or should the catalyst change the mechanism of the reaction? Or can the catalyst change the mechanism of the reaction? Or shouldn't or can't? Which is which? Or which is right and which is wrong? The catalyst can change the, you can see this is the same pathway, okay? And the catalyst can, this is different pathway, okay? This means different mechanism. This means the catalyst can, not should. The catalyst can change the mechanism of the reaction. If I ask you, should the catalyst change the mechanism of the reaction? What is the answer? Yes or no? No. Can the catalyst change the mechanism of the reaction? Yes or no? Yes. Okay. This means that it can change the mechanism of the reaction. And still, even if the mechanism changes, delta G is still the same. So we have to conclude that what we can see from this figure is delta E of catalytic reaction is much less than the uncatalyzed reaction. And delta G is the same, and the catalyst may, not should, may offer an alternative path or different mechanism for this reaction. Of course, in all cases, it is energetically less for using a catalyst. Energetically, or delta E should be less than the uncatalyzed reaction. The fourth one is, of course, I'd like to remind you about Arrhenius equation. If you remember, I'm sure you already studied Arrhenius equation, which is this form, and it can be transformed to this logarithmic form. And in this logarithmic form, of course, if you remember, you were plotting delta ln k with 1 over t. Of course, I'd like to give you an example about it. This is t values and the k values, which is corresponding to these t values. Of course, I'll not read this example because it doesn't have much information about only t and k. This is how can we solve this problem. This is solution ln k equals ln a minus e over r by 1 over t. We should calculate how 1 over t. Of course, t should be in Kelvin in this equation. Ln k, we calculate ln k and plot ln k against 1 over t. It will give a straight line. Slope of the straight line will equal activation energy over r minus, and this we can calculate activation energy from this data. Somebody may have a problem in experiment. How can he solve this problem if he could only catch only 2 points, 2 t values with 2 k values? Of course, there is a solution because you can't plot a straight line with 2 values. There is a solution which is Clausius equilibrium equation, if you remember. And this is Arrhenius equation, and this Arrhenius equation adds the second k value and t values. Of course, we subtract both values, we get Clausius equilibrium equation, and we calculate and we get the same value of activation energy. That if we have 2 values of t and k. The fourth item in the characteristics of the catalyst is catalytic cycle. What's catalytic cycle? It means what we mentioned in the beginning of this lecture. We mentioned what? We mentioned that the catalyst has a cycle, life cycle, okay? It goes once, twice, 3 times, 4 times, 10 times, 100 times, 1,000 times, million times. It may go millions of times. What does it mean? It means it may go millions of times. May go, not should go. It means that the catalyst, at the beginning, it is clean catalyst or clean surface, clean sites. After that, there is absorption of the reactants combine or bond and react with the catalyst surface like this. After that, this is absorption, this is bonding, and then after that, there is a reaction. After the reaction, of course, product will be formed, which desorbed and leaves the reaction. It's a cycle. Cycle means it is complete cycle, steps, elementary steps, complete cycle, and repeated cycle. Again, these clean sites will have A and B, and again, and again, and again. Okay. This is a cycle repeated uninterrupted. If we cut this cycle at any point, that means the process will not proceed and it will stop. Okay. This is an interpretation of what I have just said right now, and I hear the number of turnovers. We will explain about turnovers in future, inshallah. We will have what's turnover. Inshallah, we'll explain about it. But turnover means the times that the catalyst may happen at the same point or at the same site. This is the turnover. How many times? How many times it's if the catalyst may happen one time only, is this means it is a catalyst or not? One time only. It means it is not a catalyst because it's already consumed. It can't repeat again. Okay? So if it can, theoretically, if it can make 2 rounds 2 times, that means it is not consumed totally. Okay? This means it's a catalyst. But usually they consider it a catalytic reaction after turnover number with 100 or 1000 because of economics of the reaction. That's all. Not because of the main idea of catalysis. Let's go to, this is an example of catalytic cycle. This is Hick reaction. I'm sure you know about it. Aryl halide reacts with alkene to give substituted alkene in presence of a catalyst which is palladium acetoacetate. Palladium acid, yes, plus in presence of OH. This is a Hick reaction. Of course, this reaction has many lessons we have to study, and I'll try to go through these lessons one by one. The first is you can see palladium L4 means palladium complex. L means ligand, palladium with the same ligand for 4 of this ligand. This palladium L4, what can you see here? Palladium lost a ligand. Palladium lost a ligand and gave an intermediate which is palladium L3. And again lost another ligand to make a chance for aryl halide to contact with palladium, to make space for aryl halide to contact with, because it needs 2 sites. And again lost a third ligand to make a space for the alkene to contact with palladium, to make palladium and the aryl halide very close together and they can react. From here, I can ask you a very simple question. Do the catalyst react and interact with reactants during the reaction, or just keep silent and just go reactant, go and react with these reactants without touching it? Do it interact or not? Just he is a Superman with gloves and doesn't touch anybody, or he is like a woman which is put its hand inside the paste and just make it once and times and interact. It is interact. It suffers. The catalyst suffers in this reaction. It lost one ligand and another ligand and a third ligand to make a space for reactants to react, to bind to the palladium and react and give the product. And after formation of the product, which is the substituted alkene, now it starts to recover and starts to get its ligands again, starts to combine with its ligand again, step by step, until it went to palladium L4 again. Then, these are the main lessons. First, it's catalytic cycle. Each step of this is an intermediate for the next step. Each product of these steps is an intermediate for the next step. This is catalytic cycle. Of course, it's cycle. It's uninterrupted. Uninterrupted means it's continuous, uninterrupted, repeated, because it's only not only one time. It's 2 times, 5 times, 100 times, and so on. The catalyst participates in the reaction. It suffers and participates in the reaction. And formation of bonds between the catalyst and the reactants. Formation of bonds. This means there is a chemical bond is formed between the catalyst and the reactants. And the final notes is the catalyst is regenerated again. I think this scheme has a very nice and very informative information about the catalyst. This is that's what we have just said right now, that catalyst forms chemical bonds with reactants, generating intermediates that react more readily to give products. And this is an example, which is the Hick reaction. This is already discussed in previous slide. And also the catalyst is regenerated after reaction. And of course, this is also discussed about the previous slide, because it's a cycle. And finally, we will go to selectivity. What is selectivity? Selectivity means, this is the meaning of selectivity. Selectivity, it is, of course, it is the main advantage in catalysis, but it means that is the fraction of the starting material that's converted to somebody desired product. Not only product, desired product. Because if it goes to any product, this means it's conversion. If it goes to desired product, this means it's selectivity. Okay? Selectivity, of course, it's expressed. This is another expression. It is selectivity is the number of moles of product over the difference of number of moles of reactant, for example, A, which at 0 point initial concentration and the final concentration multiplied by 100, it's a percentage of selectivity. Of course, there is a very big dependency, or selectivity may characterize which catalyst is better than the other one. Because if you know, if you can see that just reaction is not the goal. The problem is how to get the desired product. If you have a reaction that gives you several products in the same time, what will you do? You have to try to separate these products. It's costly to separate these products. And you will not be able to separate it completely. Of course, this is some things about selectivity. Selectivity in catalysis is one of the most important. And we can change selectivity by changing some items, like structure of the catalyst, chemical, the chemistry of the catalyst, electronic structure, and the composition of the catalyst, and the kinetic and the energy. All of these items can change selectivity. Also, we can change selectivity by the changing preparation method. And we go to what's selectivity. There are three types of selectivity. We have 3 types of selectivity. What are these types? First is chemoselectivity. Second is regioselectivity, stereoselectivity. These are 3 types of selectivity. Of course, if you do this means if you have some dyes in water, for example, and you want to get rid of one of them, this means you can design engineering of material, engineering of nanomaterials, that you can do it and select to make a design of a catalyst that selects one dye and leaves the other components in water or something. There is regioselectivity and stereoselectivity. We will discuss about it. What's chemoselectivity? Chemoselectivity, if you have a reaction, if you have a compound like this, of course, this compound may work or may react at two positions. The first one is ketone and the ester. This one. Both these are functional groups. Of course, if we add sodium borohydride, this is selective to make reduction for a position and leave the other. As you can see here, sodium borohydride, it changed ketone to hydroxyl group. While if we use another reductant, which is lithium aluminum hydride, it goes to both of them. This means you can change the reactant position by changing the reductant you add. If you have, if you want to reduce both of these sites, you can add lithium aluminum hydride. If you want to reduce only ketone, this means you add sodium borohydride to give you hydroxide. This is the first type of selectivity. The second type of selectivity is regioselectivity. What's regioselectivity? Regioselectivity is this case. In this case, if we add HBr to this alkene, cycloalkene, what will happen? Br goes to the tertiary carbon atom and leaves mostly, not 100%. The majority will be for tertiary carbon atom, and the minority will be for secondary carbon atom. This means I just to try to select where it goes. This bromide ion. The third type of selectivity is stereoselectivity. Stereoselectivity. What's stereoselectivity? It's very simple. Cis and trans. You choose, or the reactant choose to go in for cyclohexene, for example. Bromine, when it reacts with bromine, it gives trans product, trans 1,2-dibromo cyclohexane. While in the case of cis, it is non-forming. It is not forming. The addition of molecular bromine to cyclohexene is stereoselective because only the trans bromide the dibromide is produced. This is selectivity, and here we have the activity. The catalyst should have catalytic activity, and this activity depends on different factors, like concentration of reactants, like pressure of the gases. It is the same like concentration in solution, like the temperature, and so on. However, in case of temperature, it is very special. If you add more of reactants, that means it goes to the maximum level, and then it will not have an effect afterwards. Okay? If you add more pressure, it will do the same. It will have maximum effect, and then it will be in parabola steady state, and it will not have any effect afterwards. But in case of temperature, it is different. Why it is different? It's different because temperature, of course, we know that increasing temperature 10 degrees, it changed the rate of reaction double each 10 degrees, but not all the time. How? Simply, if you working in the range, for example, 100 degrees C, it has a range for this reaction. The increasing temperature will lead to increasing the rate of reaction for double, as we just mentioned. But if we go to 200 degrees for this reaction, will the behavior be the same or not? This is a big question. Because in a range of temperature, this behavior is there. If we change the range of the studied temperature, the behavior will not be there, okay? Because increasing temperature will affect the catalyst you are using, will affect the reactants, will affect the different diffusional and properties of the thermodynamic properties of the reaction. Also, if we are using biological catalysis like enzymes or so, it will be affected by the temperature. It will, if we increase temperature, it will be deformed. Deformation will be there, okay? Deformation or decomposition of the reactants, or deformation with deformation of the enzyme. Also, increasing temperature has another problem, which is increasing cost. Temperature means energy, means money. Increasing temperature will increase the cost. I think finally the main character of the catalyst is the stability. It should be stable. It should be resistant to the environment, resistant to the reaction conditions, to be effective, to be financially effective or financially good. Because if it longs for long time, if it lasts for long time, this means it's good one. But if it just vanish after short time, this means it is not good with in the cost point of view, in the money, financial. There is another thing is regenerability. It should be regenerable. This means it is after, if it, there is something I want to tell you, that the catalyst is like the human being. It may be sick sometime. It may die one day. It may be sick sometime. This means that it is inhibited. We call it as inhibition. It is inhibited, means its activity became lower than usual. Why? It has several reasons. Like if you make a reaction of hydrocarbons, for example, and these hydrocarbons produce carbon. This carbon is like a slag, which is deposited over the active sites, which make it as capping. It just block these active sites. This means it will not work. Decreasing this active site will not work. Decreasing the number of active sites means decreasing the rate of reaction. This is sick or poisoned catalyst. Sick or poisoned, or sick or died catalyst. This is sick catalyst. I mean, it's inhibited. We can make regeneration of this catalyst again just by heating the catalyst with some air, and this air has an oxygen. This oxygen will, with heat, will react with carbon. It will form CO2 and just will leave the surface of the catalyst. Okay? You don't understand. Okay, if you have carbon, this carbon is deposited from the reaction on the active site. This means this carbon may react with oxygen to form CO or CO2, according to the ratio of oxygen present, right? If we heat the catalyst in presence of air, in presence of oxygen, this means carbon deposited on the active site will react with oxygen to form oxygen, CO2 and or CO, which are gases. Just evacuate, it will go. And the active site will remain clean. I think it's understood. This is regenerability. And another thing is for the stability and the regenerability. And if it is poisoned, poisoned means damaged. This means it's like sick man or dead man. Sick man, you can recover and just take him to the hospital. It will be okay. But dead man, you should take to the grave. That's it. Okay? Poisoned catalyst is damaged. And there are some differences between inhibited catalyst and poisoned catalyst. Poisoned catalyst means it is dyed. It is non-specific. But for inhibited catalyst, it is still sick. You can recover. And specific means something is wrong with it. You can treat it. It's like sick man. His head is not okay. His arm is not okay. His leg is not okay. You can just fix it. Okay. There is another idea I want to tell you about stability, which is there is a big difference between if you want to prepare ideal catalyst or you want to prepare real catalyst. Can you prepare ideal catalyst or not? You can ask yourself. I am sure for myself, I can't prepare ideal catalyst because no ideal, nothing ideal in this world, okay? Nothing ideal in this life. So you can't prepare ideal catalyst. Ideal catalyst means it will work in all reactions. It will give you the optimum or the desired product. It will last forever. This means nobody will have a job from the catalyst. You know, sometimes the companies make some points of the products weak just to break, and you go and buy again and buy again and buy again. This is not ideal because if you buy a car and it will last all of your life, this means these car factories will close. This is the same idea. Ideal catalyst is not there. So you can prepare real catalyst, which becomes sick and will die someday and is not going to work in all reactions and is not going to work in all conditions. This is the real catalyst. And finally, I'd like to thank you for your attention. And I hope, inshallah ta'ala, we will meet again in next lecture. Thank you very much.
Thank you, Professor Zain, for this wonderful lecture. And I hope our audience would have enjoyed this engaging lecture. And you are please welcome for any question or answer. Anyone, please? I think we can continue with question and answer session at lunch if there are no questions. And Professor Zain, moreover, he's here for 5 more days with us. So you'll have many more opportunities to interact with him. So thank you, Professor Zain, for this wonderful lecture, day one, first technical session. Thank you. Speaking on the title, features of heterogeneous catalytic processes. So please. Over to you.
Thank you very much. Thank you. Inshallah, Assalamu alaikum wa rahmatullahi wa barakatuh. Inshallah, this second lecture, I'll talk about heterogeneous features of heterogeneous catalysis. Of course, again, the title of our work is, or our proposal is, In-Situ Design and the Catalytic Dynamics of Nanomaterials for Water and Air Quality Monitoring and Mitigation. Actually, to know about catalysis, we have to know classifications of catalysis. There are different types of catalysis. The main two types of catalysis are homogeneous catalysis and heterogeneous catalysis. Just a moment, I'll try to fix this monitor. Thank you very much. Classification of catalysis, it may be homogeneous catalysis or heterogeneous catalysis. We have to understand what's homogeneous and what's heterogeneous. Homogeneous means all the components in the system or in a reactor are or have the same phase. Means gas with gas, liquid with liquid, solid with solid, and this is very rare. The second is heterogeneous catalysis, means the components in the system are different phases, like gas with solid and or gas with liquid, etc. So in homogeneous means fluid, liquid or gas. Heterogeneous means mainly solid, because once you are talking about heterogeneous catalysis, then your mind will go to different phases. Yes, but it's mainly the catalyst will be solid catalyst. Okay. There are other types of catalysis we didn't mention here, like enzyme catalysis. Enzyme catalysis, which biological catalysis, using biological catalysis. And it is the most or the oldest type of catalysis ever, okay? Because it is the since creation of this world. We can say that catalysis has industrial chemistry, or the industry depends on chemistry, has more than 90% of this industry depends on the catalysis science. More than 90%. So catalysis is the main bone or backbone of industry, really. Because if I'll give you an example, which is, for example, sulfuric acid, preparation of sulfuric acid. It is very known and very famous and very common in industry. Another very important component which is prepared by catalysis as well, which is ammonia. I'll tell you the story of ammonia very soon, inshallah. Without ammonia, maybe most of us or many of the people in this earth would suffer of hunger because of the leak of ammonia. Just I'll tell you, inshallah, because it has many applications. As I just said, that more than 90% of industrial chemistry depend on catalysis. And more than 90% of this 90% depend on heterogeneous catalysis. That means more than 80% will depend on of industrial chemistry as well, depend on heterogeneous catalysis. So what's heterogeneous catalysis? We just mentioned that heterogeneous catalysis means different phases in the reactor. Different phases like reactants or product or the catalyst, all of these have different phases. Let's see, it has many features or many characteristics or many advantages. I'll just tell you: recyclability, of course, safe to store, easy to handle, easy to separate from the reaction mixture, and they have long lifetime, avoid formation of inorganic salts, and easy and inexpensive. Also, it can be used in continuous or flow process. I'll just tell you something about the last item, which is they are continuous or flow process. We have two types in chemical reaction or reactor. It has two types. Either it's static or flow. Static means, do you remember when you were making a titration of HCl and NaCl, HCl and NaOH? This is static, means both are in the same reactor and nothing goes here or there. Or if it's under vacuum and you just add some gas on the solid, this is static. And there is another thing which is flow. Flow means some kind of liquid or gas just to go through the reaction and from one side and go out of the other side. This is flow. This can be done in case of heterogeneous catalysis, but can't be done in homogeneous catalysis. Okay, let's have a quick comparison between homogeneous and heterogeneous catalysis. I'll tell you briefly what is the difference between them, or why we use heterogeneous catalysis, why industry favors heterogeneous catalysis. But let me tell you a brief story about homogeneous and heterogeneous catalysis. What's homogeneous catalysis? Homogeneous, do you know when you add some salt, NaCl in a cup of water, what will happen? You add a spoon of salt in a cup of water. What will happen? And you just stir it little. What will happen? All the salt will distribute all over the cup of water, right? And just listen, all the salt molecules will touch can touch all the H2O molecules, right? It will be in contact. Remind this in your mind, okay? This is first. Second is, this will cause rate of reaction will be higher rate of reaction because there is a contact between reactants, and if you feel H2O is the reactant and NaCl is the catalyst. So reactant H2O will be on touch with NaCl directly. So it will cause high speed of reaction, and selectivity will be high, and efficiency of the reaction as a whole will be high. Okay, so it's good. So you have to ask me. So if you feel it's good, why don't you use it in industry? Because if I want to tell you, please separate NaCl, which is the catalyst, out of the reactants. What will you happen? What will you do? Just try to evaporate and evaporate and evaporate water and evaporate until you find a piece of salt as a residue in the cup. Okay? This is a problem. This is the main problem of homogeneous catalysis. Although it has many advantages, but it has this problem, this main problem. This main problem makes people go to heterogeneous catalysis, because even if it is less selective, less effective, less rate of reaction, but it will not cost me a lot to separate products out of the catalyst. Just if we use salt, for example, if we use, for example, sand, just add it in cup of water, what will happen? And the reaction goes and everything is done. What will happen? Please separate it. Just filtration will be okay. But in case of sodium NaCl in water, separation will not solve the problem. Okay? So let's have a look to the advantages of homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis has the same phase. Homogeneous catalysis catalyst separation is difficult, expensive and difficult to recycle. It is difficult to separate and recycle again. Requires extensive purification steps, short life, and also difficult to handle, because if I use liquids all the time, it is difficult to handle. But if I use solids sometimes, it is easy to handle. But the green color, but it has high selectivity and the high catalytic activity, low reaction temperature. It is better in these two items or three items, but it is bad in the problem is purification or separation. In case of heterogeneous catalysis, different phases, easy to separate catalyst or the product from the reaction. Easy to separate, and this is the main advantage of heterogeneous catalysis. Easy modification of the catalyst, readily regenerated and recycled, long life and less purification step, but it has low selectivity, high reaction temperature, relatively difficult of modification of the catalyst. Also, heterogeneous catalysis has a good advantage over homogeneous catalysis. For example, if you use homogeneous catalysis, water as a solvent, what is the maximum temperature you can go in this reaction? The maximum temperature is the boiling point of water. But in case of if you use heterogeneous catalysis, you can see this material may go to 100 degrees or 200 degrees or to 500 degrees or even 1,000 degrees. Whenever it can go with you, it will be okay. But in case of using homogeneous catalysis, the boiling point of solvent is controlling you. These are some examples about the heterogeneous reactions. In case of using catalyst as a liquid and reactants are the gas, like polymerization of alkane catalyzed by phosphoric acid. And this is catalyst and reactant, solid and liquid, like decomposition of hydrogen peroxide. And this is very famous reaction. The other one is if you use catalyst as solid and reactants in gas phase, like ammonia synthesis. Ammonia synthesis is one of the most important reactions, in ever known ever in chemistry. Okay. The other one is if we use catalyst as solid and reactants is solid and gas, like hydrogenation of nitrobenzene to aniline catalyzed by palladium. These are some examples of the heterogeneous catalysis. Now, let's have a look about the advantage of using heterogeneous catalysis, like this reaction. Of course, in air we have oxygen, hydrogen, nitrogen, and etc. If you have oxygen and the hydrogen together in the same bottle or in the same tube, of course they may remain for 1 year or 100 years together without reaction. You have to have very high temperature for them to react, to colloid and react. We just mentioned in previous lectures that to have effective collision, you have to have a reaction, you have to have collisions, and these collisions should be successful and should be have two factors, which are orientation and energy. Here we have to make cleavage of OO bond, which is double bond, and make cleavage of HH bond, which is single bond. These need high energy to do. In gas phase, this reaction is very slow. Even if it is thermodynamically favorable, but it will not happen. Okay. As you can see, delta G of this reaction is this amount, because it needs energy to cleave the bonds of double bond of oxygen and single bond of hydrogen, and other energy to react and so on. So what is the solution for this reaction? If you have a piece of platinum, you add only a rod of platinum in this tube that we are talking about. It has oxygen and hydrogen together. If you add only a piece of platinum, a rod of platinum, you will notice drops of water on platinum, even at room temperature. Why? Because of heterogeneous catalysis. That happened in this for this reaction. Absorption of platinum, absorption of hydrogen over platinum will cause cleavage, cleavage of HH bond, and the absorption of oxygen over platinum will cause cleavage of OO bond with nearly activation energy equals nearly zero. Nearly zero means very low. It doesn't mean zero. Okay? It's like this. If this is oxygen, and hydrogen, and cleavage occurs, and then water is formed, and water leaves the surface, and so on. In this case, it is a very fast reaction. At room temperature, it may happen with nearly zero activation energy. The other example is nitrogen with hydrogen to form ammonia. But briefly, I want to tell you about ammonia. Ammonia is the most important, nearly the most important product ever have been done by heterogeneous catalysis. Why? Because in early ages, they tried to find an alternative for organic or natural fertilizers. Because if we only depend on natural fertilizers, I think there is no food will be enough for the population in this world. Okay? Before the war and before the need of this high amount of food, it was nearly okay. But Le Chatelier, by the end of approximately 1890, 1895 in this time, tried to prepare ammonia from this reaction. First, he tried to prepare ammonia from the reaction N2 plus H2 will give NH3. And he tried, and he succeeded to prepare ammonia. But the problem is to establish or to construct a suitable reactor for this reaction. Because this reaction is tough. This reaction is very hard. This reaction needs high pressure. It needs high temperature to make cleavage of N3N and HH. It needs high temperature, high pressure, and so it needs a special reactor. At this time, he tried, and he was nearly almost succeed. And in the final step of his experiment and his design, he just exploded, and one of his team died. So he quit, just said, I will not play again in this game. And he already quit this reaction at all. After only 2 years, Haber and Bosch, those are German engineers, came and tried to establish or build this reactor, and already, alhamdulillah, succeeded to build this reactor, and they got a Nobel Prize, I think, in 1918. This last century, maybe 100 years before, because of the importance of the preparation of NH3. NH3 used is maybe it is used in 85% of its preparation is used in fertilizers, and these are some types of fertilizers prepared from ammonia, and this is ammonia uses 85% of ammonia, and this is the reaction. Ammonia N2 plus H2 gives NH3. This is exothermic reaction. It is like this exothermic reaction. It needs high energy to make cleavage of N3N and 3 H2 to give 2 moles of NH3. Okay, and some energy to complete the reaction. This is a complete system of ammonia synthesis, but I will only focus on the reactor. In this reactor, this is a compressor. This one is a compressor, and N2 hydrogen mixture with 1, 2, 3 is going through this compressor. It goes to the surface of the catalyst, which is iron catalyst, and the cleavage of these molecules occurs on this catalyst to give NH3. Then we have a mixture of NH3 plus nitrogen and the hydrogen which didn't react in this reaction. These are the mixture we have. It goes to NH3 here, and this is a cooler. Water comes goes in these tubes as a cooler, and nitrogen and hydrogen are almost permanent gases. They go to again to the system and start and make the reaction again. And the nitrogen and the NH3 will be separated from this step, as you can see here. This is a system to prepare ammonia. But for this system, what do you think? Will we need very high temperature, or will we need very high pressure, or what? I think in this mixture, of course, you know that for exothermic reaction, we consider high heat as a product in this reaction. For this exothermic reaction, what do you think? To just heat the reaction heat, then if you give it more heat, then it will go to backward reaction, or vice versa. If you give it A, it will go to C plus D. If you supply it with C or D, it will return back to A plus B, and so on. This is Le Chatelier that we were talking about Le Chatelier. And by the way, he, after the problem of ammonia, he published an article later, and he just said that he made a mistake to leave this problem, and he denied or regret to leave ammonia synthesis slipped from his hand. He published a paper after 5 years from maybe 1905. Anyway, here heat is considered as a reactant-like concentration, reactants and products and something like this. Okay. In this reaction, H2 plus nitrogen equals NH3 plus some heat. In this exothermic reaction, by Le Chatelier principle, as your friend just said, that if we affect this reaction by adding temperature, of course, it will go in the reverse direction. But if we just cool it, it will go to forward direction. And this is simple this is each one of them. The amount of ammonia with temperature at different pressures, at 1 atmosphere, 3 atmosphere, until 300 atmosphere. We keep pressure constant, but we change the temperature. Of course, if we change the temperature, this means, as you can see here, that from higher temperature to lower temperature, as you can see, at 500 degrees, the amount of ammonia was very high. If we keep at 300 atmosphere, the amount of ammonia was very high. And if we increase temperature, the amount of ammonia decrease. If we take any other one at 10 atmosphere, the amount of ammonia decreases with increasing the temperature. If we establish the temperature at constant temperature, for example, at this temperature, if we go up at different pressures, what will happen? Increasing pressure leads to increasing the amount of ammonia comes here, because as you can see, you can 1.5 mole of hydrogen plus 0.5 mole of nitrogen to give 1 mole of NH3. This means pressure decrease in this reaction. Means if we increase the pressure, it will lead to decreasing the pressure, and the reaction will go forward. Okay, I think it is understood. And this is another story of decreasing the temperature at different pressures like this. As you can see, if we keep the pressure at 200 by increasing the temperature, by increasing its temperature, the amount of ammonia decrease. And here, this energy to make collisions and complete the reaction. Because we can't only decrease the temperature to room temperature. At this time, there is no reaction will occur. Because we need some energy to make collision and to overcome activation energy. The role of catalyst, this is the role of catalyst, that it makes heterogeneous catalysis. It makes absorption of hydrogen and of nitrogen together very close to each other to have a chance to colloid, to have a chance to react. It's like if you have your friend, either you can discuss with anybody, just to go to some place like restaurant or like cafe or something, just to take a table and two chairs and sit and discuss. It is the same. Like nitrogen goes to active site, just beside hydrogen in the beside active site, and they are very close to colloid and they interact together and they give NH3. Now we will have another example of heterogeneous catalysis of heterogeneous reaction, which is N-hexane reaction over the platinum and in presence of hydrogen at very high temperature from 500 to 700 degrees C. Now I'll tell you what will happen, and I will have a question after my explanation. Here in this reaction, it may make aromatization. It may make cyclization to give aromatization to give benzene, cyclization to give methyl cyclobentene. And it may make isomerization. Another possibility, it may make hydrogenation to give propane. This reaction, of course, we just add N-hexane and add platinum as a catalyst and just flow hydrogen at high temperature. In this reaction, what do you think? Does it have good selectivity or bad selectivity? If you understand what I have just said in previous lecture. Bad selectivity. Why does it have bad selectivity? Because because it have several products. We don't know how much it is, and we will have so much time and the effort to separate these reactions. On the other hand, if we check this catalyst in syngas is a mixture of CO plus hydrogen, synthesis gas. Okay, in syngas, for example, if we add syngas together in presence of copper, all of these are heterogeneous catalysts as well. It will give us formaldehyde. However, if we add the same mixture in presence of other catalysts like nickel, of course, it will give CH4. Another story, if we have iron and cobalt together, it will give alkane. There is another possibility, if we have copper with zinc, chromium, it will give methanol. A fourth or fifth possibility, rhodium cluster, it will give glycol. What do you think about selectivity in this reaction? I think selectivity is perfect because it's a key. If you want to have alkane, just to go to iron and copper. If you need methane, just to go to nickel. If you need, for example, methanol, just to go to this mixture of oxides. Okay, this means it is good selective, has high selectivity, and all of these are heterogeneous catalysis. This means you can see all of these are sources of power, sources of energy, all of these sources of very important chemicals. All of these are becoming, or all of these are obtained from heterogeneous catalysis. Let's go to, okay, thank you very much. I think it's a short lecture, and I am happy to finish it. Thank you very much.
Is there any question from the audience? You can ask anything.
Okay. Thanks, Professor Zain, for the valuable lecture. I hope the lecture is beneficial for you all. And if you have any queries, any discussion, please discuss. Okay. Thank you very much.
Once you don't have came here to Delhi, and always I like Indian culture and in Indian history. But Al Azhar is much more ancient or earlier than many places ever, and all his old Egypt and the history of Egypt is much similar than history of India. And this is Al Azhar has in its scientific part Al Azhar tries to teach the engineer religion besides engineering, try to teach the doctor medical science beside religion science, tries to teach scientists like in chemists or physicists or something like this beside religion science. So I think mentally it's good for those people, and also scientifically it's very good university. I hope I just briefly introduced Al Azhar University for you. If you have any question about it, I am here. It's my pleasure to answer you.
Can you please tell them some opportunities from today Al Azhar University for
Yes, of course. In for Al Azhar University, if you go to website of Al Azhar, you will find many scholarships are introduced to foreigners. If you apply, I am sure you can get a chance, because as far as I know, a lot of scholarships are it introduces a lot of scholarships for Muslims to go there and study in Al Azhar. But it is in undergraduate level. But I am not sure about postgraduate level. I'm not sure about it. If I'm sure it is there, but is it as a scholarship or it is paid? It's paid study. I am not sure. But what I am sure is for undergraduates there are a lot of scholarships Al Azhar introduces for foreigners, and many students are coming from Indonesia, India, Malaysia, and Pakistan. Many people are there.
is there any exchange programs are also for the graduate students?
For graduate students,
Exchange program, some kind of exchange program is there?
yes, we have collaboration with many people, but exchange program like there is MOU or not, I'm not sure, but we can check it.
आपको के पास कोई भी graduate पूछ सकते हैं because Al Azhar University is one of the most prestigious universities in the world, biggest university in the world, and have lots of facility for the research. If you people go for higher education, it will be really beneficial for all. That's why I was asking. अगर आपकी कोई भी query है, please पूछ लीजिए. We are fortunate to have a great scientist like you, and we can directly interact with you. If you have any doubt or any question, please ask. अपने career से related to he has visited many universities in the world. He has knowledge about many universities in the world. So please.
Okay, later when they just check, and we can have a tea together, inshallah, and everyone will ask whatever he wants. I am here for you. For you. You are the princess and the queen and the prince. You are the most prestigious and the most important persons in this class. Not me, not Professor Rice, not Professor Slim. You are the most important. So we are here for you. You're welcome. Okay.
This is only the first day of initiation. Since lots of students traveled today, that's why we are not giving tutorial today. So it is a relaxation for the tutorial only for today. From tomorrow onwards, you will find your tutorial just after the class, and you have to submit the tutorial in your next day. And in the end of the day, end of the sessions, you will find a small test online. So please do not worry. You have to pass the exam also. It will be easy and basic. And can you please raise your hand who is outside of Jamia?